All right, so we're going to start Unit 5, which kicks off with a section on inverse functions. So inverse functions, we need to define what they are, right? They're the function that undoes another function, if you want to think about that, or a function's opposite. In order for a function to have an inverse function, it must be one-to-one, so we're going to talk about that. We're going to talk about how to find the formula for an inverse function algebraically, and then we're going to look at some application problems involving inverse functions, okay? So when we look at an inverse function, basically we can take any relation and swap its input and its output. So that's what this is saying. If we have a relation R, then we can find the inverse, R inverse, by the set of all ordered pairs BA such that AB is originally in our R relation, okay? So basically what we need to know is that we're swapping all of our inputs and our outputs, okay, or all of our X's and our Y's. And this results in a mirror image of the original graph over the identity line, okay? So I'm going to skip this example for just a second, and I want to show you what this looks like graphically so that you have kind of an idea. So we're going to use x cubed as an example. So I'm just going to pick some random points so we can get a good graphical representation of x cubed. So if I take -2, -1, 0, 1, and 2, and I plug them in and cube them, I'm going to get -8, -1, 0, 1, and 8. Okay? So I want to graph this so that I can see what this cubic function looks like. So at -2, I'm down at -8. At -1, I'm at -1. 0, I'm at 0. 1, I'm at 1. And 2, I'm back up at 8. So when I connect my dots, this kind of makes a little whoosh that's kind of jogged over in the middle, okay? And now I want to find its inverse function. Well, our inverse is defined to be all the ordered pairs of our original relation, but swapped, right? So if I take all of these original points and I swap them, that should give me my inverse function, okay? So I'm going to go ahead and swap them. That's going to give me -8, -2, -1, -1, 0, 0, 1, 1, and 8, 2. So all I did was make all the x's my y's, and all of my y's are now my x's. So I just swapped them, okay? So now I want to regraph this and see what it looks like. So at -8, I'm down at -2. -1, I'm at -1. 0, I'm at 0. 1, I'm up at 1. And 8, I'm up at 2. So notice when I connect these dots, I'm still getting that same shape that I got originally, but now it's kind of going the opposite direction. And notice in our definition here, it says that when we graph our inverse, it results in a graph that is the mirror image of the original graph over the identity line. So the identity line is y equals x. That's where all of our x's and y's are equal. So that would be this line that goes straight through the origin, right? So notice if I take this blue function and flip it over this dotted line, notice this little piece is reflected across over here, right? And then this blue piece going down is reflected across to the red piece over here. So this is a really great way to check yourself whenever you have to graph a function and its inverse. It should create a mirror image across this identity line. And the reason that it does that is because we're going from one graph to its inverse by swapping all the x's and y's, which is what creates that mirror image, okay? Now, if we are given a relation, just a set of ordered pairs like this example, and we're asked to find its inverse, all we do is the same thing, right? We just swap all of our ordered pairs, all of our x's and our y's. So given that S is the set 1, 2, 3, 4, -5, -6, if I want to find S inverse, it would just be the set of all the same ordered pairs, but with the x's and y's swapped. So it would be 2, 1, 3, 4, negative 5, negative 6, or sorry, negative 6, negative 5 for our inverse relation, okay? All right, so there's one at the bottom of the page for you to do. I'm going to go ahead and give you a minute to find the inverse of R. So you're looking for R inverse. And this is just notation, okay? When we talk about an inverse function or an inverse relation, using the little -1 exponent means we're talking about the inverse, okay? This does not mean 1 over R. This does not mean 1 over S, okay? It's just notation. So go ahead and pause the video, figure out the inverse set, and then we'll go over it. Okay, so to find the inverse relation, all we have to do here is take all the ordered pairs that were given to us in the original relation and swap their x's and y's. So we should have the set of points -2, -1, 8, 7, 0, 0, 4, 3, and -6, -5. Okay, so far so good, just swapping points, not too bad. Now I want to look at them graphically, okay? There is something cool about looking at them graphically, because in order for a function to have an inverse, it has to be what's called a 1-to-1 function, okay? 1-to-1 function. That's our shorthand notation for this, okay? And what that means is every element of the range, or our y values, right, must be paired with exactly one element of the domain. So we're going to use what's called the horizontal line test. So let's just kind of reflect, right? When we reflect, we've talked about the vertical line test. If a function is to be a function, right, every x can only have one y value. And so that's why we use the vertical line test, is to make sure there's no x's repeated, right? That's what makes it a function. But now we need to make sure that there's no y values repeated, because if I have 2 of the same y values, then when I swap all my x's and y's, I'm now going to have 2 x's, right? Because I originally had 2 of the same y. When I swap it, that's going to give me 2 of the same x, which then will not pass the vertical line test. So instead of going through the whole process we did on the last page of like getting a table of values for the original function and then swapping them and then graphing to see if it passes the vertical line test, we're just going to do a horizontal line test, because a horizontal line test checks to make sure there's no y values repeated. And if we know that there's no y values repeated on the original function, then when we swap all our x's and y's, we shouldn't have an issue, okay? So that's all we're going to do, is if we look at these functions, this one is the little swooshy x cubed, right, that we just went over on the last page. Notice if I draw a horizontal line anywhere on here, it's only going to hit at one point. So if it only hits at one place, that's good. That means it passes the horizontal line test, which means that yes, it should have an inverse, okay? We're going to do the same thing on the next ones. Notice this is the little half parabola. The little half parabola was the square root of x, okay? These are shapes we should know. And this one, if I draw a horizontal line anywhere on here, it's only going to hit one place. So that's great. It passes the horizontal line test, which means that yes, this one has an inverse. Okay. When I look at a parabola, however, notice if I draw a horizontal line anywhere on here, it's actually going to hit twice. So that's a fail, right? Because whatever these y values are, when I swap my x's and my y's, that's actually going to create like a parabola that looks something like this, right? And that's not good, because that's not going to pass the vertical line test. So if it fails the horizontal line test, then we know, no, this is not going to have an inverse. Okay, so there's 3 for y'all to try. I'd like for you to identify the function, if you know it. Oh, I forgot to put this one was an x squared, right? Figure out what the basic function is, if you remember the shape, and then tell me yes or no if it has an inverse. Okay, so go ahead and pause it, give that a go, and then we'll go over it. All right, let's go ahead and go over them. The first one, notice this is the other one we did on the first page. On the very first page of this section, we did an x cubed, and then we swapped all the values and ended up with this shape. So you can think about what undoes an x cubed is actually a cube root. So this is our cube root function. And if I draw a horizontal line anywhere on here, you can see it's only going to hit one time. So yes, it should have an inverse. right? And this one's just a regular straight line. Now, it's been moved up, and we could count the slope and figure out the function, but its basic parent function is just an x, right? This is just some version of y equals x that, you know, has a certain slope and a certain y-intercept. Any positive or negative sloped line should have an inverse, because if I draw a horizontal line anywhere on here, it's only going to hit at one place, okay? All right, and then our last one here, we have this nice V shape, and that V shape comes from an absolute value. Now, obviously, this one's been flipped down and moved up, but the basic shape is an absolute value. An absolute value is going to give us problems, because if I draw a horizontal line, notice just like our parabola up here, it's going to hit in two places. So no, this one does not have an inverse. So you will have some problems that will say, does this function have an inverse? And you can just answer yes or no. So the only ones that we would answer no on are our parabola and our absolute value. Everything else we've gone over looks like it should have one, right? If you're not sure, then just do the horizontal line test. If it passes, then yes, it has an inverse. If it fails, then no, it doesn't, okay? So pretty much any x squared function and any absolute value function is not going to pass the horizontal line test as it is, right? But I have this note down here that says some functions that don't normally have an inverse function may have a specific domain restriction, okay? So that they may have an inverse function, meaning if I were to look at this absolute value and I said, hey, I'm just going to look at this little teeny tiny piece from here down. If I look at just that little teeny tiny bold piece from here down, would that little piece pass the horizontal line test? Well, it would, right? Or maybe if I take this parabola and I only look at this half of it, this side of it, this bold piece, right? Would that by itself pass the horizontal line test? And it would. So if you're given just a regular x squared or absolute value, you can say, no, it doesn't have an inverse. But if they have restricted the domain so that the piece that is left, or the piece that you're actually considering, passes the horizontal line, then it is possible for a parabola or an absolute value to have an inverse, okay? So we're going to look at some specific examples and see if we can determine if a function has an inverse. Now, we don't have to do all this extra work unless it's a parabola or an absolute value, okay? If they give us a function that's a cube root, a cube, a square root, or some version of just x to the first power, we can just say, yes, absolutely it has an inverse, because we know that those will always pass the horizontal line test, right? All right, so let's look at some of our problems. On this first one, we have f of x is equal to x minus 3 squared plus 2 for x's that are greater than or equal to 3. So notice this one's giving us a domain restriction, meaning if that wasn't there, if we just had f of x equals the squared quantity plus 2 and it says, does this have an inverse? My answer would be no, because I know that that little squared is going to make a parabola, and a parabola will not pass the horizontal line test, okay? But since there's a domain restriction, then hey, maybe it will pass, okay? So I'm just going to quickly review our HSRV way of transforming functions so that we can get a good picture, and then we'll look at our domain restriction, okay? So this is a x squared, so I'm going to start off with a parent table for a parabola. Now remember, our basic parabola is at the origin and then it just increases on both sides, right? Or sorry, it continues on up from both sides. So I'm going to go ahead and pick a negative, a 0, and a positive, just so that I have that good parabola shape. Because if I just pick positives, I'm only going to get that one side, right? If I just pick negatives, I'm only going to pick the other side. So I want to make sure I have a good representation. Now if I plug these numbers into my squared function, I'm going to get 4, 0, 4. So this is my parent table, and now I need to do a table for each thing that has changed this function from looking like just x squared. So I'm going to list my HSRV, and I can see here that I have a minus 3 on the inside, right? A minus 3 on the inside. X's are backwards. And so that's actually going to be a horizontal shift to the right 3. Remember doing this? Bringing back all those happy memories. Okay, so this is where we're going to take our X's and we're going to add 3 to them to shift the thing to the right, right? And then our positive 2 is outside the function, so that's being applied to the Y's. And when we add 2 to the Y's, that's going to be a vertical shift up 2. So I'm going to take my Y's and add 2 to them. Okay, so no stretching, no reflecting. So I'm going to do these in HSRV order, meaning I do my horizontal shift first. So now my function looks like x minus 3 quantity squared. And to adjust my table, I'm going to take my x's and add 3 to them. So x's from the previous table, I add 3. That's going to give me a 1, 3, 5, and my y's stay the same. So 4, 0, 4. Then I want to go ahead and shift it vertically up 2. So now my function looks like x minus 3 squared plus 2. And to move it vertically up 2, I'm going to take my y's from the previous table and add 2 to them. So that's going to give me 6, 2, 6. And then my x's stay 1, 3, 5. Okay, so I have my picture. Let's go ahead and graph it. So I have 1, I'm up at 6. 1, 2, 3, 4, 5, 6. At 3, 1, 2, 3, I'm up at 2. And at 5, I'm back up at 6. So this is what my parabola looks like, right? Okay. Now, normally this parabola would not have an inverse, right? Because I can draw a horizontal line and it's going to hit more than once. But specifically, they're restricting our domain to x's that are greater than or equal to 3. So I'm going to go over here and look at where 3 is. 1, 2, 3. Here's where x equals 3. And I'm starting at x equals 3. And since it says x is greater than or equal to, I'm going to include the point at x equals 3, and then I'm going to look at everything to the right, right? Because everything greater than. So from this point where x equals 3, and then everything to the right side. So that would be this whole side of this parabola. So if I look at just this half of the parabola that starts at x equals 3, notice this piece by itself does in fact pass the horizontal line test, right? So because we had a domain restriction that basically cut off this half of the parabola, and I'm only talking about this piece, then yes, this is going to have an inverse, okay? And I'm just going to say because with the domain restriction, the graph passes the horizontal line test. Okay, so it has an inverse because with that little restriction, this little piece that we're talking about passes the horizontal line test. Okay, all right, so I'm going to skip this next one, and I'm actually going to do the first practice problem. And then when I give y'all ones to do, I'm going to have y'all come back and do this one. Okay, so let's go ahead and look at the first practice problem here. I'm going to do this one as an example. Okay, and then the one on page 4, I'm going to make this our first practice problem. Okay, all right, so for this one, again, I have an x squared. X squared makes a parabola, which normally does not have an inverse function, but I have a domain restriction. So I'm going to see if this restriction is enough to cause this to have an inverse. So I'm going to list out my HSRV, and I see that I have 2 transformations, right? I have the negative in front of the x squared, and I have the plus 3. Now, a negative in front of the x squared because it's not included in parentheses, right? If there was parentheses around this negative x, then it would be inside the function. But since there's no parentheses, that means this squared is not being applied to that negative, which means that the negative is outside the function. So if the negative is outside the function, that means it's being applied to the y's. So we're negating the y's. And when we take all of our y's from being positive and make them all negative, that's a reflection around the x-axis. So that's an R about the x-axis. And we got that because we know we're changing the signs of our y's. Okay, so that was our transformation on this little negative. Now I want to look at the plus 3. The plus 3 is not inside a squared quantity, so it's also outside the function. And a positive 3 outside the function represents a vertical shift. So this is going to be a vertical shift up 3. So I'm going to take all my y's and add 3 to them. So no horizontal, no stretching. Okay. All right. So again, I'm doing a parabola. Parabola's basic form is an x squared. I'm going to use negative 202 again, just so that I have a negative, a 0, and a positive. And when I square those, that gives me 404. And then I'm going to do my transformations in HSRV order. So I'm going to go ahead and do my reflection first. So my reflection is going to make this look like a negative x squared. And we're going to change the signs of our y's, which makes this negative 4, 0, negative 4. My x's stay the same, negative 202. And then I'm going to move it up 3. So now my function looks like negative x squared plus 3. And the way that I move it up 3 is I take my y's from the previous table and I add 3 to them. So that's going to give me negative 1, 3, negative 1. And my x's stay negative 202. Okay, so I'm going to go ahead and graph this last table. So at negative 2, I'm down at negative 1. 0, I'm up at 3. And 2, I'm down at negative 1. Okay, so this should give me a pretty decent parabola picture. Okay, now this normally would not pass the the horizontal line test, right? But I was given a domain restriction. So looking at this domain restriction, we're going to go ahead and modify our graph. So this says we're looking at x's that are greater than or equal to negative 1. So greater than or equal to negative 1. We go where negative 1 is, which is right here. And we're going to the right because we want greater than that number. So starting at wherever that hits, which we're going to say is right there, okay, and I'm using a closed dot because it's greater than or equal to. If this was a strict greater than, then I would use an open circle at that point, okay? But it's closed, so I'm including that, and then I'm going to the right. Any of this parabola to the right, which is going to be this whole piece, right? I'm going to go ahead and make this super bold. All right, so looking at this entire piece that starts at negative 1, would this entire piece right there pass the horizontal line test? It doesn't, right? Because if I were to draw a horizontal line anywhere up here where I still have the little top of that parabola, it's going to fail, right? So this one, no, does not have an inverse because it fails the horizontal line test. Okay? All right. So again, we only have to do this if we're starting with a function that we know doesn't have an inverse. So if we started with like a cube or an x or a square root or any of those, we don't have to go through this whole process. We could just say, yes, they have an inverse. They always have an inverse. But if we start with a parabola or an absolute value, something we know fails the horizontal line test, then we need to go through this process of graphing it, identifying the piece that we're considering with the domain restriction, and then determine, does that piece satisfy the horizontal line test, okay? So I want y'all to take a minute and work on the two problems, the practice problem, the last example on page 4, and then number 2 on page 5. Okay, so go ahead and pause it and try those, and then we'll go over them. Okay, so looking at the last example on page 4, this is an absolute value which normally does not pass the vertical line test, or sorry, oh my gosh, the horizontal line test, and therefore we need to go through and see if this domain restriction is enough to make it pass the horizontal line test. So starting with an absolute value, you know this is a V that the point is at the origin and it goes out in both directions, right? So we need to make sure we pick a negative, a 0, and a positive. And when we plug those into our absolute value, everything comes out positive. So negative 2, 2, 0, 0, 2, 2. That's what I'm going to start with. And then there's been 2 shifts. The +4 on the inside is a horizontal shift to the left. The -1 on the outside of the function is a vertical shift down 1. So we're just going to modify our tables to do our horizontal shift and then our vertical shift down. Once we do that, then we identify the piece that satisfies this domain restriction, which is x is less than -2. So we put on our graph where -2 is, and we're starting at that point and then going from the left. So 2 things I want to point out. 1, because this is a strict inequality, that means we're not including the point at -2. So notice I have an open circle at that value. And then 2, when we take from that open circle the rest of the function to the left, we still have a little bit of the tip of that V, right? And as long as we have any piece of that V, it's not going to pass the horizontal line test. And you can see here where the x-axis cuts it and you get 2 points. So it fails the horizontal line test. So this one does not have an inverse. Okay. All right. On the practice problem, the second practice problem, you actually didn't have to go through the whole process. If you did, your function would look something like this, but you don't actually have to do all of this on this one, because if you notice right away that it's an x cubed, x cubes, no matter how much you stretch, shrink, shift up, down, left, right, they will always pass the horizontal line test. Okay, it's only with parabolas and absolute values that we have to modify with a domain restriction, right? So you didn't have to do all of this. You could have just said, yep, it has an inverse. Okay. All right. So now I want to move on to solving for the inverse. So we've talked about what an inverse is. We've talked about what it means to be one-to-one. We've talked about looking at a graph and performing the horizontal line test, and then also how to modify with a restricted domain. What we're going to look at now is actually finding the inverse algebraically, and then also being able to find the domain and range of that inverse. Okay, so here's our process. Our process is we want to determine whether or not the function has an inverse. So just looking at it. If we just look at it and we see it's a cube root, we know it has an inverse, so we keep going. If we look at it and it's like an x squared and there's no domain restriction, then we can just say there is no inverse and we don't have to solve for it, right? So just determine by looking at it whether or not it should have an inverse. And then we're going to replace our f of x with y. This is so that we just take it out of function notation so that we can actually see x's and y's in our problem. Okay, so once we have it written with y's instead of f of x's, then we're going to swap all of our x's with all of our y's, because remember, that's how we get the inverse. We swap our ordered pairs, right? So in the function, we're just going to see everywhere we see an x, we're going to put a y. Everywhere we see a y, we're going to put an x. Okay. Once we've swapped them all, then we're just going to resolve it for y. And then once it's resolved for y, that gives us our inverse function. So we want to make sure that we write it with function notation. Okay. All right. So let's go ahead and look at some. Now it says we want to find the inverse function, right? And we also want to find the domain and the range. So I'm going to go ahead and first I want to think about what this looks like, because in order to find the domain and range of our new function, we need to know the domain and range of our original function. Okay, so our original function is a square root function, and a square root function looks something like this, right? And then it's modified, because normally it starts at 0, 0, but we can see here there's been a couple of transformations. We have the negative out front, we have the +1 inside. So if I were to do my HSRV, and I'm not going to go through the whole process, I'm just going to get a quick sketch. the positive 1 underneath here, that's going to move it to the left 1. And then the negative that's outside the function, that's negating the y's, which is going to reflect it about the x-axis, right? So no stretching, no vertical shifts. So if I take my original picture of a square root function and I move it to the left 1, okay, then instead of it starting at 0, 0, it's going to start back here at -1, right? Because I'm just shifting it back to the left 1. Then I'm going to reflect it about the x-axis. This is the x-axis, so that's going to flip it down, okay? So again, it's still going to be starting here at -1, but now it's going to be flipped down. So this is what my function looks like. So off this little sketch, I should be able to figure out what my domain of my original function is and what my range of my original function is. So my domain is my x's, right? These are the x's, range is the y's. So my original x's that I can use for this function don't start until I get to -1. So I'm going to go ahead and put -1. I'm using a bracket because it's included. And then my x's continue on out to the right, with this arrow tells me it's going to keep going and going. So -1 to infinity is where I have x values for this function. Then I'm going to look for my y values by finding the range. So range, we do our lowest y value up to our highest y value. So our lowest y value here, this is going to keep going down and down and down and down, right? So this is going to go down to -infinity. But the highest point on this function is this point right here, right? It's going to go from -infinity up to this y value. And the y value of this point is 0. So -infinity to 0. Okay, so this is the domain and range of my original function. And I'm going to need those in order to find the domain and range of my inverse function because, remember when we find our inverse, we're just taking our x's and our y's and we're swapping them, right? So if the domain is our x values and the range is our y values, then all we have to do is swap the domain and range in our inverse function. Okay, so we'll do that in just a minute. But let's go ahead and work through how to algebraically find that inverse. So we know this is a square root function. It passes the horizontal line test. So number 1, check, it should have an inverse. Number 2, we're going to take it out of function notation. So I'm going to write this as y is equal to -square root of x plus 1. And then our next step is to swap all of the x's with all of the y's. So I'm going to write down here, we're just going to swap. Now once I swap it, now we're talking about the inverse function. So we have x is equal to -square root of y plus 1. Everywhere there was a y, I'm writing an x. Everywhere there was an x, I'm writing a y. Okay? And now I need to solve this for y, which is right now stuck inside the square root. So I first need to get the square root isolated by getting rid of this negative. So I'm just going to divide by -1 on both sides, which gives me a -x is equal to a positive square root of y plus 1. And then I need to get rid of the square root so I can get y by itself. So to undo a square root, I square it. If I square that side, I have to square the other side. Okay. So on the left side, square root of a negative becomes, not square root. When I square a negative, it becomes positive. So this just becomes x squared is equal to, when we square a square root, they cancel, and I'm left with y plus 1. And then the last thing I need to do to get y by itself is move this 1 to the other side by subtracting. So I have x squared minus 1 equals y. And now this is my inverse function. So my last step is to write it back in function notation. So this says that my inverse function, f inverse of x, is equal to x squared minus 1. And then we need to write the domain of my inverse function and the range of my inverse function. Okay. The domain of my inverse function, that's the x's, right? So remember, the x's of our new function we got originally from the y's of our original, right? So in other words, my y's become my x's and my x's become my y's. So I'm just swapping from the original domain and range to get my new domain and range. So that means my new domain is my original range, which is -infinity to 0. And my new range is my original domain, which is -1 to infinity. Okay, so there's my inverse function and its domain and range. Okay, let's look at another one. Same idea. So we start off by determining, does this have an inverse? It's a cubed, so yes, cubics should have inverses. Remember, cubics are our little swoosh function that we did at the very beginning of this section, right? And then we need to identify our shifts. So if we do our little HSRV, we can see that the -2 on the inside, that's going to move us to the right 2. And our +7 on the outside is going to move us up 7. So no stretching, no shrinking. So to move it to the right 2, 1, 2. Now it's going to look something like this, right? If we move it over. And then up 7, 1, 2, we're just going to pretend here's 7, is now it's going to be something like this, right? So off of this little sketch, I should be able to figure out what my original domain is and my original range. Okay, my original domain is how far is this going to go left and right? Well, the arrows in both directions are going to tell me that, you know, it keeps going in both directions. So -infinity to infinity. And my range is how far up and down this function is going to go. So notice it's going to keep going up and down in both directions. So the range is also -infinity to infinity. And actually, when we deal with cubics, this is the one we actually don't need to go through all these steps, because any cubic function has a range that keeps going and going and going up and down, and a domain that keeps going left and right. No matter how much we stretch it, shrink it, reflect it, move it up, down, left, right, it's always going to have this domain and range. Okay? All right, so now let's go ahead and jump in and find our inverse function. So we're going to take our original function, take it out of function notation. So we have y is equal to the quantity x minus 2 cubed plus 7. And then we're going to swap all of our variables. So everywhere we see a y, we're going to put an x. Everywhere we see an x, we're going to put a y. And now we're going to resolve this for y to get our inverse function. So first thing I need to do is get the cubic quantity isolated, because that's where my y is. So I'm going to move my 7 over. So I have x minus 7 is equal to the quantity y minus 2 cubed. And now I need to get rid of this cube that's on this quantity. So to undo a cube, I'm going to take the cube root. So I take the cube root of x minus 7, and I take the cubed root of y minus 2 cubed. So I just have the cube root of x minus 7 on the left, and on the right, my cube and my cube root cancel, and I have y minus 2. And then the last thing I need to do to get y by itself is move that 2 to the other side. So I have the cube root of x minus 7 plus 2, right? Changes signs when I move the 2 from one side to the other, is equal to y. And now that it's resolved for y, this is my inverse function. So I'm going to go ahead and write this as f inverse of x is equal to the cube root of x minus 7 plus 2. And then we're going to go ahead and list our domain of our inverse function and our range of our inverse function. So just like we did on the first one, right, our domain comes from our original range, and our range comes from our original domain, so we swap them. In this case, they're both the same, so we can't really tell if we swapped them or not, but it's good to mention. All right, okay, maybe not the worst thing. I want to do a couple more examples, and then I'm going to let y'all try some, okay? All right, let's go ahead and take a look at the next one at the top of the next page, and it is a squared function. So we know normally this does not have an inverse. So we're going to go ahead and do a little sketch over here to the side to see if this domain restriction is getting rid of enough of it that it would pass the horizontal line test. So I'm going to go ahead and just sketch here that normally a parabola is centered at the origin, right? That's where our vertex is. And then if we look at our HSRV, right, I can see the -1 on the inside is going to move us to the right 1, and then the 4 outside the function is a vertical shift up 4. So no stretching, no reflecting. So if I move this parabola to the right 1, now the vertex is going to be over here at 1, right? It's going to look something like that. And then we're going to move it up 4. So now vertex is still going to be lined up at 1, but we're going to go 1, 2, 3, 4, up 4, and our vertex will be going up from there. Okay? So this is what it looks like. Normally does not pass the horizontal line test. So we go ahead and look at our stipulation, which is that we're only considering the piece where x is greater than or equal to 1. So here's where x is equal to 1. So we're including that point. And then x is greater than or equal to 1 means we're looking at the right side of this function. Okay? So looking at just that bold piece, so not this piece, just the bold piece, now that's something that would pass the horizontal line test, right? So now I want to go ahead and take this and find my domain and range based on just that piece. That means that our domain of this function, right, which is our x's, right? Domain is our x's. The furthest to the left this bold picture goes is x equals 1, and it's included because we have an equal to bar on our inequality here. And then this is going to continue going out to the right because of the arrow. So 1 to infinity for our domain. Then we look at our range of our original function, which remember is our y's. So the lowest y value we're going to have is at this point, which is at 4. So lowest y value is at 4, and then notice it's going to continue on up to positive infinity. So that's our original domain and our original range. Now we need to go ahead and identify what our new inverse function is and its domain and range. So I'm going to go ahead and write this out of function notation. So we have y is equal to x minus 1 quantity squared plus 4. And then we're going to swap all of our variables. So when we swap, we're now going to have x is equal to the quantity y minus 1 squared plus 4. Okay, and now we need to solve this for y. Y is stuck inside this squared quantity, so we need to move our 4 to the other side to get that quantity isolated. So quantity y minus 1 squared. And then to get rid of the square, we're going to take the square root of both sides. So I have the square root of x minus 4 is equal to the square root of y minus 1 squared. So we have the square root of x minus 4 is equal to y minus 1, because the square and the square root cancels, right? And the last thing I need to do is move my 1 to the other side. So I have the square root of x minus 4 plus 1 is equal to y. And now that it's solved for y, this is my inverse function. We were dealing with an f of x originally, so my inverse function is going to be f inverse of x, which we just found to be the square root of x minus 4 plus 1. Then we're going to list our domain of our inverse and our range of our inverse. Okay, so remember the domain of our inverse is our original range. So that's going to be 4 to infinity. And then the range of our inverse is our original domain, which in this case is going to be 1 to infinity. Okay, not too bad. All right, let's look at one more. Now this one's a little bit different because we didn't go over how to graph rational functions. So we can't just really quickly sketch a picture, but we should be able to, even without a picture, find the domain. We did go over how to find the domain of a rational function. And remember, domain deals with the denominator. we know that the denominator cannot equal 0, right? Because that gives us a restricted domain value, right? Or an undefined denominator. So if I set this equal to 0 and solve, that means that 2x cannot equal -1. And then I divide the 2 off, which means that x cannot equal -1/2. So we have figured out that the domain of our original function can be anything except -1/2. So the way that we write anything except -1/2 in interval notation is from -infinity to -1/2, and then -1/2 to infinity. Okay. Now, range is going to be a little bit different, so we're going to not worry about the range for just a second, and we're going to move on to finding our inverse function. So I'm going to write this without the f of x. I'm going to write it with y is equal to x minus 3 over 2x plus 1. And then I'm going to swap all of my variables, right? So that gives us x is equal to y minus 3 over 2y plus 1. If you had x's on top and bottom, you should now have y's on top and bottom. So make sure you swap everywhere there's an x with everywhere there's a y, okay? All right, and now we need to be able to solve this to get all our y's on the same side, right? And the way that we can do that is by clearing this denominator. So to clear the denominator, we just take that denominator and multiply both sides by it, okay? So I'm going to go ahead and do 2y plus 1 times x on this side, right? And 2y plus 1 times my y minus 3 over 2y plus 1 on that side. So all I'm taking is this bottom quantity and multiplying both sides by it. That way it will cancel on the right-hand side, okay? I'm going to go ahead and distribute this out. So this gives me 2xy plus x is equal to y minus 3. And now I'm a little bit closer to being able to solve this for y. To solve it for y, I need all my y terms on the same side. So I'm going to move this y term over here by subtracting. And notice that gets my y terms on the same side. And since I'm solving for y, that's all I want on this side. So I'm also going to move this x over to the other side because I don't need it. It doesn't have a y. Okay. So that's going to give me 2xy minus y is equal to -3 minus x. Okay, so all the y terms to one side, all the x terms to the other side. Okay, and now I can't combine these y terms because one has an x and the other one doesn't. But I can always get y by itself by factoring it out like a greatest common factor. So I'm going to take out the y, which leaves me with 2x minus 1 is equal to -3 minus x, and then I just divide off this quantity. So I'm going to divide off my 2x minus 1 so that I get y all by itself. Okay? So that means that y is equal to -3 minus x over 2x minus 1. Since it's solved for y, this is my inverse function. So I'm going to go ahead and say f inverse of x is equal to -3 minus x over 2x minus 1. Now again, I don't know how to graph this, right? We didn't go over that. Well, I mean, I know how to graph it, but we didn't go over how to graph rational functions, but we should be able to find the domain of this new function the same way we found the domain of the original, right? All I have to do is look at the denominator, and for my domain, I just have to say that 2x minus 1 can't be 0, and then I solve it for that restriction. So if I move my 1 over, that means that 2x cannot equal 1, and then I divide the 2 off, which means that x cannot be 1/2. Okay? So for my new function, my new domain, my domain of f inverse, it can be anything except for positive 1/2. So the way that we write it can be anything except for positive 1/2 is to say that it can be from -infinity up to 1/2, and then 1/2 to infinity. Okay, and then to find the range of my inverse, remember the range comes from the original domain. So the original domain here was -infinity to -1/2 and -1/2 to infinity. Okay, And the cool thing about it is, remember how we couldn't find our original range because we, aren't graphing it? Well, just like we can figure out these two by taking from the original, we can find the originals by taking from the inverse. So if I'm looking for the range of f, that's going to be the domain of my new function. So now I know what the range of the original is. It's got to be negative infinity to positive 1/2 and positive 1/2 to infinity. Okay? All right, so on the next page, there are two for you to try, which I'd like for you to do. Pause the video, and then whenever you're ready, or if you get stuck, go ahead and play the video, and we'll go over it. All right, so when we go over this, the first thing we want to do, because this is an x squared or a parabola function, right, a quadratic, we need to make sure that our domain restriction is strict enough to take care of the fact that this is not going to pass the horizontal line test, right? So we start out with a basic parabola whose vertex is at the origin. We can see that our shifts here were to go left 2 and up 1. So if I move it left 2, it's now at -2. And then if I move it up 1, now this vertex is at -2, +1, right? And since we want x's that are strictly less than -2, we're using an open circle at that point, and we're looking at the piece that goes to the left, okay? So looking at just this piece, we can see that it will pass the horizontal line test, so that's great. So based on just this little piece, we're going to go ahead and state our domain and range. Because this is an open circle, we should be using parentheses, okay? So our domain is from negative infinity up to where my x's stop, so negative infinity to -2. And then my range is my lowest y value, which is at 1 with an open circle, on up to my highest y value, which should go up to infinity, okay? Then we want to go ahead and solve for our inverse. So we take it out of function notation by writing it with a y, swap our variables, and then solve. So we need to move the +1 over by subtracting, then take the square root of both sides to get rid of the squared on that quantity, and then move my +2 over. Okay, so that gives me my inverse function, which is the square root of x - 1 - 2. And then to figure out my domain and range of this new function, I take the domain and range of the original and just swap them, right? So we end up with a domain of 1 to infinity, a range of negative infinity to -2. All right, let's look at number 2. Same thing here. Again, we're not graphing this to figure out domain and range, but we can find the domain by just figuring out what the denominator can't be. In this case, it's -2. So our domain on the original is from negative infinity to -2 and -2 to infinity. Then we find our inverse function by putting y in for f of x and swapping all of our variables. Once we have it swapped, we want to get rid of this denominator by multiplying both sides by y + 2. That way the y + 2 cancels off on this side, and I'll just have x times y + 2 on the left. We distribute the x in, and then we want to get both of our y terms on the same side. So I'm going to move my 3x to this side by subtracting, and then I'm going to get rid of this term that doesn't have a y by moving it to the other side by subtracting. Once my y's are on the same side, I can factor out the y and divide off the leftovers. So this is what our inverse function should look like, and then we want to make sure we write it back in function notation. And then just like we did with the original, finding the domain, we can figure out what would make this denominator 0 to find the domain of our new inverse function. So if I set that equal to 0 and solve, I get 3. So it cannot be 3. So the domain of our inverse is all real numbers except for 3. And then we know the range of our new function because it's the domain of our original. Okay, and then vice versa. Now that we know the domain of the inverse, we should know the range of the original. Okay. All right, so another cool thing that we can do with inverses is we can verify that two functions are inverses by composing them. So remember back when we were composing functions, f composed with f inverse means I'm taking f inverse and plugging it into that outside function, right? Or plugging f inverse into f. The cool thing about plugging a function into its inverse is everything should simplify out to where it just equals x. Same thing if you do an inverse composed with the original, it should all simplify down and just equal x. Okay, so that's how we can prove that two functions are inverses, by just composing them both directions and showing that it equals x. So I want to show you one, and then I'm going to have you try one. And I put a little note here because normally I don't put these as test problems, but maybe as like extra credit problems, things like that. So it is good to be able to know how to do this. Okay, so first I want to verify that f composed with f inverse of x actually equals x. So what this is telling me to do is this is telling me to put this x into my inverse, right, which is just my inverse function, and then we're going to plug that into the outer function. Okay, so I'm plugging f inverse, which is 7 over x plus 1, into my other function. So I'm going to go ahead and write this. This means I'm plugging in 7 over x plus 1. That's what's going into my original function. My original function says to do 7 minus my input and divide it by my input, right? So I'm putting in 7 over x plus 1 for my input. 7 over x plus 1, 7 over x plus 1. Now this should simplify down to x if these are in fact true inverses. So I'm going to go ahead and use our little shortcut. Remember how we can multiply everything on top and bottom by the same value? It's like multiplying by a form of 1. So the thing that I want to multiply everything by is x plus 1. So if I multiply this by x plus 1, and I multiply this by x plus 1, and I multiply this by x plus 1, it's like I'm multiplying by x plus 1 on top and bottom, which is a form of 1. So I'm not changing the value. So what I end up with is here I can distribute this, right? I have 7x plus 7, and then here my quantities will cancel, and I'll just be left with a minus 7. On bottom, my quantities will cancel, and I'm just left with a 7. And then notice 7 and negative 7 combine to 0, so I'm left with just 7x over 7, which is indeed just x. Okay, so that's showing it one direction. Now I want to show it the other direction because both have to be true in order for it to be an inverse. So this was f composed with its inverse. Now we want to do the inverse composed with the original. So in this case, we're taking the original and putting it inside the inverse. So f inverse with the original put inside. So I'm going to go ahead and write what the original function is. The original function is 7 minus x over x, right? And that's what I want to put into my inverse. My inverse function says to do 7 divided by my input plus 1. And notice our input here is 7 minus x over x. Okay, so just like we did on the other one, I want to figure out what would clear all my denominators, which in this case is just an x. So I'm going to multiply by an x up here, I'm going to multiply by an x here, and I'm going to multiply by an x here, right? That way, on top, I'll get 7x. On bottom, here my x's cancel, and I'll just have 7 minus x, and then my second term is a plus x. Okay. So notice the negative x and the plus x are opposites, so those combine to 0. So I end up with 7x over 7, which again is in fact x. Okay. All right, so there's one for y'all to try. I just want you to show that f composed of its inverse equals x, and f inverse composed with the original equals x. Okay, so go ahead and pause the video whenever you're done, or if you get stuck, go ahead and unpause it and we'll go over it. Okay. Okay, let's see how you did. So on the first one, when we do f composed with its inverse, we are plugging the inverse function, which is x plus 2 quantity cubed over 3, into our f function. So notice our f function says we're going to do the cube root of 3 times our input and then subtract 2. So when I do 3 times our input, my 3's actually cancel, right? So I would be left with the cube root of my cubed quantity, and then my cube and my cube root cancel. So I'm just left with the x plus 2 that was underneath it and the minus 2 that was outside. The 2's are opposites, so that becomes just x. Same thing in the other direction. This time I'm plugging in my original function, which is the cube root of 3x minus 2. I'm plugging that into my inverse. So my inverse function says to take my input, which is this whole mess, plus 2, right? And then cube it and divide it by 3. So here, I can actually drop my parentheses that I had put around this, and my negative 2 and my positive 2 cancel out. So I'm just left with the cube root of 3x cubed. Cube and cube root cancel, which leaves me with 3x over 3, which then again is just x. So you just have to verify it both directions to show that two functions are inverses. Okay? All right, the last thing I want to cover is a couple of word problems, a couple of application problems involving inverses. Okay? So if I look at this first one on page 10, it says, swimming lessons. A city swimming league determines that the cost per person of a group of swim lessons is given by this formula, where x is the number of people, that's important, x is the number of people in the group, and c of x is in dollars. Find c inverse of x and explain what it represents. Okay, well, before I can explain what the inverse represents, I have to make sure I know what the original represents. And here it says x is the number of people. So in our ordered pair, we have the number of people in the group, right, that we're plugging in. And then our function is telling us the cost in dollars. Okay, right? So this is what my original c of x represents. So if I want to figure out what c inverse represents, these would be swapped, right? All right, so let's go ahead and figure out what c inverse is. So I'm going to take my function c of x, which is equal to 60 plus 2x over x, and I'm going to make it so that I don't have function notation. I'm going to write a y here. So I have y is equal to 60 plus 2x over x, and then I'm going to swap all my variables. So when I swap my variables, I end up with x is equal to 60 plus 2y over y. Okay, so again, I want to clear my fractions, so I need to get rid of this y in the denominator. So I'm going to multiply this side by y, and I'm going to multiply this side by y. So when I multiply both sides by y, that y will cancel out on the right-hand side. Okay, so that leaves me with xy is equal to 60 plus 2y. Then I need my y terms on the same side, so I'm going to take this 2y and subtract it to the other side. So xy minus 2y equals 60. And then I can get the y out by factoring out like a greatest common factor. So that leaves me with x minus 2 is equal to 60. And then to get y by itself, I just need to divide off this x minus 2 quantity. So I end up with y is equal to 60 over x minus 2. And remember, this is my inverse function. So I need to go ahead and label it with c inverse of x. So c inverse of x is equal to 60 over x minus 2. And what does that represent? We're supposed to explain it. I'm fine with you just giving an ordered pair. If the original, we plugged in the number of people and we got out the cost for the swimming lessons, then the inverse is going to do the opposite. We would plug in the cost and we would get out the number of people in the group. Okay? All right, let's look at one more and then I'll have y'all try one. Okay? This one's talking about converting temperatures, and it says the following formula can be used to convert Fahrenheit temperatures X, so X is Fahrenheit temperatures, to Celsius temperatures T of X. Celsius temperatures is our output. So what this is telling us is that our T of X function takes Fahrenheit temperatures, right, because that's what X is, and converts them to Celsius. So it takes Fahrenheit and makes them into Celsius. So right now I can stop. I know exactly what this represents. This goes from degrees Fahrenheit to degrees Celsius. Okay? So let's see what part A wants us to do. It wants us to find T evaluated at negative 13 and T evaluated at 86. So that just means we're taking those numbers and plugging them into this function. So for part A, we're going to evaluate T of negative 13 degrees. And again, this is Fahrenheit, right? We're trying to convert it to Celsius. So when I plug it in, my function says to do 5/9 times my input, which is negative 13, minus 32. So negative 13 minus 32 gives me a negative 45. And 9 actually divides into negative 45. 9 goes into 45, or negative 45, negative 5 times. And then 5 times negative 5 gives me negative 25 degrees. And now it's in Celsius. Okay? Then we want to do the same thing for T of 86. So T evaluated at 86 degrees Fahrenheit. We plug it into our formula, which says to do 5/9 times our input, which is 86, minus 32. Here, 86 minus 32 gives me 54. And again, 9 divides evenly into 54. 6 times, right? 5 times 6 means this converts to 30 degrees Celsius. Okay, so part A wasn't even talking about the inverse, it just wanted us to evaluate the function. Okay, part B, however, says we want to find the inverse function and explain what it represents. So I'm going to first write my function, my original, with a y instead of a T of X. So I have y is equal to 5/9 times x minus 32. And I'm going to swap all my variables. So once I swap it, that gives me x is equal to 5/9 times y minus 32, right? And I'm solving for y, and it's stuck inside this quantity. So I first need to get this quantity by itself. So I need to get rid of 5/9. So in order to get rid of 5/9, I'm going to multiply by the reciprocal. So I'm just going to multiply this side by 9/5 and multiply this side by 9/5. So that way these will cancel. So I end up with 9/5 x is equal to y minus 32. And then the last thing I need to do is move that 32 to the other side by adding. So I have 9/5 x plus 32 is equal to y. And now this is my inverse function. Since my original function was called T of x, we're going to call this one T inverse of x. And we know that it equals 9/5 x plus 32. And it didn't just ask me to find it. It said find T inverse of x and explain what it represents. So if my original function, T of x, took it from Fahrenheit degrees to Celsius degrees, then that means my inverse function is going to take it from Celsius to Fahrenheit, right? So we're going to go ahead and just say this goes from degrees Celsius to degrees Fahrenheit. I wrote the degree on the wrong side. There we go. Degrees Celsius to degrees Fahrenheit. Okay? All right, on the next page, there's one for y'all to try. So go ahead and pause the video and try that one. And then when you're ready, we'll go over it. Okay, so when you start these problems, you want to make sure you know what the function represents before you ever start trying to find the inverse. Okay? First, it says the total amount of spending per year in billions of dollars on pets in the United States X years after 2000 is given by this function. So that told us everything we need to know. Okay, the total amount of spending per year in billions of dollars on pets in the US X years after 2000 is given by this function. So it says X years after 2000. So we already know that X is representing the number of years. So when we plug in the number of years, what this function is telling us is the total amount of spending in billions that is spent on pets, right? So this is billions of dollars, okay? So once we know what our function is representing, then we can go ahead and move on and see what they want us to do. Part A says determine the total amount of spending. So they want to know the output, so they should be giving us an input. Determine the total amount of spending per year on pets in 2005 and 2010. Now remember, X is the years after 2000. So in 2005, 5 years has passed since 2000. So we would plug in a 5, and that gives us 36.191. Now remember, our output is the number or the cost in billions of dollars spent on pets. So that means $36.191 billion was spent on pets in 2005. Okay, then we do the same thing for 2010. 10 years have passed since 2000, so we're plugging a 10 in, and once we plug in 10 and simplify, that means $47.082 billion was spent on pets in 2010. Okay. Then part B says find the inverse and explain what it represents. So before I even find it, I already know what it represents because it does the opposite of what the original did. So if the original allowed me to plug in the number of years since 2000, so basically it gives us the time, the years, and we get out the cost of $1 billion that was spent on pets, what the inverse function is going to do is it's going to allow me to put in the amount that was spent on pets and determine the year in which that happened. Okay, so to find the inverse function, I write it without the function notation, I swap my variables, and then I solve for y. So I just move the 25.3 over and divide off my coefficient. So this is my inverse function, and all I had to do was swap what my ordered pair represented. Okay. All right, so that is the end of section 5.1. You should now be able to complete the My Math Lab assignment corresponding to this section. If you have any issues or need help, please let me know.